In the previous lecture, we have developed the generalized theory of small oscillations. In fact, we have obtained the general equation of motion for small oscillations, and today our aim is to solve that very equation of motion. Actually, when you will solve the equation, you will see that we will have a secular equation that secular equation, when solved, we get the eigenvalues and eigenfunction of the matrix in the equation of motion. So I am just starting this lecture with the previous result of which we have learnt in the previous lecture. You have seen that in case of a small oscillation of a system, when we have applied the Lagrange equation of motion to obtain the equation of motion, then the final result, that is the final equation of motion for small oscillations which we have obtained, was like this. This is summation over I1 to n Tij ui double dot plus Vij ui equal to 0. I hope you can remember this result, because this was the last result of the previous lecture on generalized theory of small oscillations. Okay. In fact, in this equation, you know, this Tij, these are actually the elements of symmetric matrix T, and this was actually for the constant coefficient of the Mij in the quadratic form of kinetic energy expression. And since it is a symmetric matrix, so this Tij is equal to Tji. And this Vij, which was the coefficient in the expression of the potential energy function, these are actually the elements of the symmetric matrix V, and since it is a symmetric matrix, so Vij is equal to Vji. Okay. In fact, we try to find the solution of this very equation A in oscillatory form. So writing the solution of that very equation in oscillatory form like this: ui equal to Cia e to the power I omega t. In fact, in this equation, you know that this ui is actually the coordinate. This is displacement of our system from the equilibrium position. Okay, you have learned these things in the previous lecture. And this Cia is the complex amplitude of the oscillation. Okay. In fact, I have written this complex amplitude just not like Ai, but Cai. Here C is actually called a scale factor. In fact, this scale factor has been used for convenience, and it will have the same value for all coordinates, that is all values of ui. Okay. And omega is the frequency of oscillation. Okay. And I here in the exponent of E extends for a square root of -1, that is, this is iota. Okay. And here this subscript I is for a number, that is 1, 2, 3, 4 and so on. Okay. So don't confuse these two I, because when you write I as an exponent of exponential factor, then it is actually for imaginary, and when you write it like a subscript, then it represents a number. Okay. Now in our equation A, there are two functions. This is ui and ui double dot, and we have defined already this ui, but we have to know the value of ui double dot. So we will simply differentiate 2 times the value of ui which we have obtained with respect to time to get the value of ui double dot. So let us see here that this ui is equal to this much defined in equation 1, and so to get the value of ui double dot, first of all, let us find ui dot. When you say ui dot, you know that this is simply dui by dt, and that will be what? since CAI is a constant factor, so only this e to the power I omega t will be differentiated with respect to t, and that will be I omega times e to the power I omega t. Now, ui double dot, it means we will have to differentiate this dui by dt again with respect to t, and that is d2 ui by dt square, and that will be I square omega square CAI e to the power I omega t. Now I square, you know, this is equal to, in fact, minus 1. So this is minus omega square CAI e to the power I omega t. Okay. Now we will put the value of this ui defined in equation 1 and ui double dot defined in this equation 2 in this equation A, which is our equation of motion. Okay, at the place of ui double dot and ui, we will substitute them. So after substituting those two values, what will be our result? You can see easily. This will be summation over I Vij CAI e to the power I omega t minus omega square Tij CAI e to the power I omega t, and that equal to 0. Okay. Now you can see that this C e to the power I omega t is a common factor and it is independent of the summation. So we take it outside from the summation and as a common factor. And inside the summation, the terms will be Vij AI minus omega square Tij AI, and that is equal to 0. Now you know that C is a scale factor, it is arbitrary, and so it is not 0, and e to the power I omega t cannot be 0 at all time. So it may be 0 or may not be 0. So in general, you can say that this e to the power I omega t is not 0 in general. But our result is 0. So definitely the second factor inside this square bracket with summation must be 0. And so I have written here that summation over I from 1 to n Vij AI minus omega square Tij AI equal to 0. Now if you want to write this equation 3a in matrix form, you know that the matrix associated with this Vij is written like V, and with AI we will write it A, and with Tij we write it T, and again with AI with A. Okay. So this in matrix form, this equation can be written as Va minus omega square Ta equal to 0. And this can be written as V minus omega square T times A equal to 0. Actually here this V and T both are actually n by n matrices. You can see I have defined these two matrices in this manner. This V is a n by n square matrix and its elements are V11, V12, V1n, and similarly Vn1, Vn2, Vnn. So this is just a n by n matrix. Similarly, this T is also an n by n matrix defined like this. You can see it here. Okay. Now, this A is just a column matrix and it is defined like A1, A2, An. Okay. So when we will substitute these matrices in this equation which we have obtained, which is actually called secular equation, this is V minus omega square Ta equal to 0. So let us substitute the matrices associated with V and T, V, T and A in this equation 3b. Then you can see after substituting these matrices, our result will be like this. That is matrix V minus omega square matrix T operated on this column matrix A1, A2, so on An, and that will be equal to 0. Now this matrix equation can be written in terms of n linear equations. You can see this will be V11 minus omega square T11 operated on A1 will be equal to and plus V12 minus omega square T12 operated on A2 plus and so on V1n minus omega square T1n operated on an, and that will be equal to 0. In this way, you can write V21 minus omega square T21 operated on A1, and that will be equal plus, and similar terms you have to write. And so you can see I have written that these equations, the equations contained in that matrix form will be equal to this. This is V11 minus omega square T11 A1 plus V12 omega square T12 A2 plus so on plus V1n omega square T1n an equal to 0. And in the similar manner, the last nth equation will be Vn1 minus omega square Tn1 A1 plus Vn2 minus omega square Tn2 A2 plus so on plus Vnn minus omega square Tnn an equal to 0. Okay. Now, if we assume that the inverse of matrix T exists, when you say that the inverse of matrix T exists, it means T inverse exists. So let us multiply this equation 3b. See here, this equation 3b here by the inverse of matrix T, that is T inverse from left side. So what will be the result? You can see this will be T inverse V minus omega square T inverse T, okay, A equal to 0, okay, because in RHS there is 0, so when you will multiply 0 by T inverse, that will be again 0. So you can see I have multiplied that equation by from left side by the inverse of matrix T, and this is T inverse V minus omega square T inverse T A equal to 0. Now you know that T inverse is the inverse matrix of T, so T inverse T will be simply equal to I, which is called inverse unit matrix. And we also assume that this T inverse V is equal to P. You can see I have written it here. T inverse P, we assume that this is equal to P. So that equation can be written like this. This is P minus omega square I A equal to 0. In fact, this equation you can write like this. This is P A equal to omega square I A. This is just an eigenvalue equation. Here P is the operator or the matrix operated on the eigenvector A, and the result is omega square A. Okay, so this omega square is the eigenvalue of the matrix P or the operator P, you can say. Okay, and A is the eigenvector. Okay, so I have written here that this is an eigenvalue equation, and omega square are the eigenvalues of matrix P, and A is the eigenvector with n components. In fact, this A eigenvector will have n component. We will see this later on. Okay. Now, after getting this eigenvalue equation, now we will try to solve this eigenvalue equation. You know that whenever we want to solve the eigenvalue equation, we have to write the secular equation. Secular equation means this determinant of this P minus omega square I should be equated to 0. Okay, and when you say that P minus omega square I equal to 0, in other words, you can also say that this V minus omega square T is equal, determinant of V minus omega square T is equal to 0 from this equation. You can see here from this equation. Okay, and Now this secular equation can be now solved uh, like this. Now you know that this matrix V is actually n by n matrix, so that equation can be written as V11 minus omega square T11, V12 omega square T12, and so on, V1n minus omega square T1n, and similarly the nth term will be Vn1 minus omega square Tn1, Vn2 minus omega square Tn2, so on, Vnn minus omega square Tnn equal to 0. Okay. And as I have told you that this very equation which I have written in this equation number 4 is called a secular equation. The page is turning, but it will be okay, don't be worried. This is just okay now. See here, this is called secular equation. Okay, and now this secular equation, you can see that this is actually an equation of degree n for omega square, because in this equation there are n by n in this equation is in the form of n by n matrix. So you can say that this is an equation of nth degree for omega square, and so there will be n roots of this equation. N root means we will have the n values of omega square. Okay, and those n values of omega square, if you assume, are omega 1 square, omega 2 square, omega, and so on, omega n square. Actually, these frequencies are the normal mode frequencies. Okay, so it is clear that whenever a system will be displaced slightly from its equilibrium position and then the system is released, the system performs a small oscillation or a oscillation with a small amplitude about the equilibrium position, and we will have the n discrete frequencies defined by omega 1, omega 2, and so on, omega n. And that's why the solution of this secular equation is often called the frequencies of free vibrations. These omega 1, omega 2, omega 3, so on, omega n, which are the solution of the secular equation, these are called frequencies of the free vibrations. Okay, or they are also called resonance frequencies. Okay, now since you have seen that the frequency, the solution of the secular equation actually gives us n values of omega, that is n frequencies. So in this condition, we can write the general solution for the summation of these frequencies. And so the general solution is written like this: ui equal to summation k1 to n ck aik e to the power I omega kt. Here the subscript k has been used for summation for the different frequencies and corresponding amplitudes. Okay, corresponding amplitudes. For the kth mode of vibration, if you assume that the frequency is omega k, then summing up for all the frequencies, we get the resultant displacement of our system. Okay, and here actually the ith component of the amplitude, which is written like AK, this is just a column matrix given like this: A1k, A2k, Ank. So you can see that each AK has n values. Okay, and there are n eigenvectors. So as a whole, you can say that there are n by n eigenvector components for the system, and those n by n eigenvector for the system then can be written as A equal to A11, A12, so on, An, and so just like that, an1, an2, so on, ann. Okay. So in this condition, for the oscillatory system, there are n eigenvectors, and those eigenvectors are a1, a2, so on, ak and an, and ak has actually n values. So in this way, you can say that there will be total n times n eigenvector components for the system. The total number of eigenvector components for the system will be n into n. Okay, and those values are written in this equation 7. Okay, now as you can see that for each solution of omega k square of that circular equation which I have defined in equation 4, there are actually two resonant frequencies. Omega k square will have both plus value, that is plus omega k, and minus omega k. But the eigenvector ak will have the same values for the two frequencies. Okay, but eigenvalues ak are same, but the scale factors for plus omega k and minus omega k may be very different. So we consider that the eigen vector for both of these frequencies, plus omega k and minus omega k, are ak, but the scale factors for them are ck plus and ck minus. It means for plus omega k frequency, the scale factor is ck plus, and for minus omega k it is ck minus. We assume that. So in this condition, if you want to write the general solution of the oscillatory motion, then that will be written like this: ui equal to summation over k aik ck plus e to the power plus I omega kt plus ck minus e to the power minus I omega kt. Okay. Actually, the actual motion of the motion is written by the real part of this complex solution of the equation of motion. And you know that the real part of e to the power I theta is cos theta. So when we write in practice the real part of this complex solution, we simply write it like this. This is ui equal to summation over k fk aik cos omega kt plus phi k. Here these fk and phi k has been introduced. Actually, the values of these constants are obtained from the initial conditions or boundary conditions. So this is the general result for the solution of the equation of motion of a small oscillation. But this is a general theory. These facts will be clear to you only when you will solve the particular physical problem. When you will solve the particular physical problem, then you will see how we calculate the eigenvalue, how we calculate the eigenvectors, and how we find the general solution in that condition. That is finding the value of fk and phi k. What is the actual solution of that physical problem, you will see. So after solving some important problems or some illustrative examples, this general theory of a small oscillation will be clear to you. And I will provide some of the illustrative examples in the forthcoming lecture of this series. Okay, so thank you very much. I hope you have enjoyed this lecture too. So watch the video seriously, write down into your notebook, and then everything will be clear to you. Okay.